In this video, we're going to continue our talk about energy. And first, we're going to talk about the idea of internal energy. And internal energy is simply the sum of kinetic, that is movement, and potential energies in all the particles of our system, whatever we define our system as. And internal energy is what we call a state function. That is, the change in energy is only dependent on the initial and final states. So when you see this delta sign, that means change. And when we do change, it is always final minus initial. And so if we're looking at the change in energy of a reaction, its products are final states minus reactants, our initial states. Now, like I said, state functions, the change in energy only depends on your final and your initial states. And so let's think about this example question. We have two different trails to get up this mountain. Path A, which is 12 miles and a switchback, and Path B, which is only 5 miles, but it's steeper. If we're going up 10,000 feet in both cases, which path has a greater change in our potential energy? And the answer to that is the potential energy is going to be the same. Energy is a state function. It doesn't matter if we go on path A or path B. All that matters is we start at 0 feet and we end at 10,000 feet. That's what a state function means. It doesn't matter how you get there, it just matters your final and your initial states. So let's think about energy flow now in a chemical reaction, because this is chemistry class. Remember, law of conservation of energy, energy cannot be created or destroyed. So the reaction copper plus oxygen goes to carbon dioxide, not copper. Now, for reasons we don't need to get into, 1 mole of carbon and oxygen have a greater internal energy than 1 mole of carbon dioxide. Since energy can't be destroyed or created, when this reaction happens, this energy has to go somewhere. So our reactants are higher energy than our products. Therefore, we release energy into the surroundings, and the surroundings heat up. So this is an exothermic reaction, because our system are our molecules, and we have lost energy and we gave it to the surroundings. And the way we measure this is that the change in energy of our reaction is equal to the negative change of the energy of our surroundings, because the same amount of energy is being exchanged. It's just that one side is gaining energy and the other side is losing energy. For example, in our reaction, we lost energy, and that same amount of energy was gained by our surroundings. That's why we have that negative sign here. And so we can either talk about energy flowing into the system or out of the system. If energy flows into our system, then the change of energy is positive. Therefore, the change of energy in our system is negative. If it's the reverse, if energy flows out of our system, like we saw in our carbon and oxygen example, the change in energy in our system is negative. The change in our energy of our system is positive, and energy flows the other way. So whatever way, if energy flows into you, that change in energy is positive. So let's just check our understanding here. So think about this question. What statement is true of the internal energy of the system and its surrounding following a process in which delta E system is 65 kilojoules? Take a second and pick one of the answers. Alright, the answer is D. So our system has a positive number, so it gains 65 kilojoules of energy. And since we gain energy, the surrounding must lose the same amount of energy, 65 kilojoules of energy. And when we talk about energy exchange, it's really hard to measure energy, like energy itself. Instead, we have to talk about heat and work. Heat we call Q, work we call W. Now, these aren't state functions. Both heat and work do depend on the path you take, but adding them together will give you delta E, which is a state function. So let's just look at the signs. So if we have positive heat, we gain thermal energy. Negative heat, or Q, we lose thermal energy. Positive work has been done on the system, on us. Negative work done by the system. Delta E, energy flows into the system. Negative delta E flows out of the system. So again, I have a problem here for you to check your understanding. So identify each energy exchange as primarily heat or work, and determine whether the sign of delta E is positive or negative for the system. And so take a minute and try to figure this out. Alright, so sweat evaporates from the skin, cooling the skin. So that's heat. And if our sweat is the system, delta E is positive because heat went into it. So a balloon expands against the pressure. That's work. And if the balloon is our system, then work is negative. The change in E is negative because we're pushing against the atmosphere. So we're doing work. The system is doing work. All right. And a reaction is warmed by external flame. Again, that's heat. Our energy is positive because the heat is flowing into our system. All right, one more problem. So we have gas in the piston. The piston is our system. It warms and absorbs 655 joules of heat. We do 344 joules of work on the surroundings. What's our change in internal energy for the system? Again, see if you can figure this one out. Come back if you have an answer. All right, let's take a look at it. First, we have to define what our change in energy is. Delta E equals Q plus W. We have a Q, 655. We have a W, 344. Now we have to determine the signs of Q and W. So since we absorb heat, that's a positive value. We do work, that's a negative value. So it's 655 minus 344 equals 311 joules. So we actually gain energy through this process. Alright, that's it for this video. I'll see you in the next one.